Özlem, and I will be delivering like two of the lectures this week, and also Sabah will be with you in two of the lectures. We will start at this time. Wait, maybe we have 5 more minutes until start. Is it true?
Yes, we have 5 more
Okay,
minutes.
okay, let's wait then. I thought for a second that we were like 5 minutes late. Okay, then let's wait.
That's okay. So welcome to the first session of our QBronze workshop, and thank you very much for your interest in this workshop organized in cooperation with EuroCC-Turkey and QTurkey team. And we also thank you very much in advance for your active participation. We wish all of you a nice and productive week. And I would like to thank all my colleagues and QTurkey team who contributed to the organization of this workshop. And we would like to thank Dr. Özlem and Dr. Sabah for accepting our invitation. And let me introduce Dr. Özlem. She's a computer science researcher at Algorithmic, a Finland-based startup developing quantum algorithms for life science. Previously, she worked as a postdoctoral researcher at the Institute of Theoretical and Applied Informatics of the Political Academy of Science. She obtained her PhD in computer engineering from Boğaziçi University in 2019. And recently, she has been working on modeling and solving combinatorial optimization problems using quantum optimization algorithms. She is one of the founders of QTurkey, a non-profit organization popularizing quantum technologies. And she has organized and instructed quantum programming workshops and developed open source educational materials to promote quantum computing. And in the session, Dr. Özlem will talk about classical bits, probabilistic states, and probabilistic operators, and also quantum programs as circuits. So I will leave floor to the Dr. Özlem. Thanks so much again.
Thank you very much for the introduction. It's really a nice chance for us to be involved in this event. We are really happy to be here. So this week, together with Sabah, we will conduct QBronze workshop of QTurkey, which is an introductory quantum programming workshop. So there were some questions about recordings of the previous lectures to start with. So you can find all necessary information on the event page. Here is a link for the previous recordings. And here you also see the schedule of the rest of the workshop, and also a link for the material. But I will shortly also go through Discord to give you necessary information you will need for this to follow this workshop. So you should have received an email to join this Discord of the event. And here you will see some channels, and within those channels there is all the necessary information. If you click material, you'll see the link for the repository of the Jupyter notebooks we will use in this workshop. And you should download this material, like clicking here, and then you can download the zip version. And then you will find here inside installation necessary instructions for installation. And like we also have channels, for instance, like setup help. So to follow this workshop, you need to install like Jupyter notebooks, Qiskit, and so on. But if you like face any problems, you can write here, and we have some mentors who will assist you. So you can write any questions you have if you have any problems in installation. We will also share here like Zoom links, recordings. If you have any questions, you can also write here. Like there are many channels like material help, Python help, homework help, and so on. You can use the Discord like efficiently. Just write if you have any questions. Another issue is about the homework. So to obtain a certificate at the end of this workshop, you need to complete some homeworks within the given time, and you need to score at least like 70 overall. So over 100. So we have 5 homeworks, and each one is over 20. And you can unlock the next homework after you score at least 10 from each one of them. So overall, the requirement is that you score at least 10 from each homework, and in total you score at least 70. And this is Canvas, and you should also have get an invitation to join Canvas, where you will submit your homework. So you have like there will be some multiple questions, multiple choice questions. And I suppose you should have like unlimited number of attempts and highest score is taken. And for each homework, you have a deadline, which you can see here, like December 25, December 26, and so on. And again, if you have any problems, if you didn't receive a link, if you cannot log in, etc., you can also write in Discord. Let me also quickly give you some information on QTurkey. We are the first, and I suppose only quantum technologies related network in Turkey since 2019. We are organizing different events involving quantum programming workshops, online talks, like some on-site events where we like bring together people from academia. We have a YouTube channel, and on our YouTube channel you can find many interesting talks on quantum technologies. We have a blog where we share like news in Turkish about like quantum technologies, and also there are some like original articles here. So you can also have a look at this page. You can follow us on Twitter and LinkedIn, on other social media platforms. And like this week we will be following QBronze, which is the introductory level workshop. But we also have intermediate and advanced level workshops called Q-Nickel and Q-Silver. And you can follow us to get tuned and join those workshops as well. The prerequisite is to have a bronze certificate to join those other workshops. You can also follow QWorld. So Q-Turkey events are sometimes in Turkish. And sometimes we organize events together with other which we call like cousins with other countries. Those events are in English, but QWorld within QWorld there are some cousins which are also organizing events in English, and you can see all our events listed here. So if you like would like to get in touch with us, you can also write us. Here you will find a contact form. So I suppose that's all I would like to say before we start. Do you have any questions before we move on? I suppose no. Then I think we can start. Uh, so today, this is the plan. We will start with classical bits, then move on to probabilistic bits. And finally, you will see an example of a quantum circuit. So let me give you basic idea of our material bronze. So this is the main page. So you should go to this page once you are done with the installation, which gives links to all the notebooks inside the material. This first part is if you need some like review on basic math involving matrices and so on, and basic Python like lists, variables, conditions, etc. And today we will cover this part until Qiskit basics. So this material bronze consists of Jupyter notebooks in which there is some theory and also there are some practice tasks. Let me give you an example. Here, like you see some stuff, you should read this, and then you should complete the tasks below if you want to fully understand what's going on. So we are not going to check if you complete those tasks or not, but this is highly recommended. So to follow the material and complete those tasks. And all tasks has come with their solutions. You can click here to get the solution. And if you don't understand something, you can write in Discord. So we really advise you to complete the tasks because this is how you understand what's going on. And homework is something like separate from this. Homeworks are multiple choice questions. And in this material bronze, we will not go into complex numbers. We will only work with real numbers. If you have already some experience in quantum computing, you know that complex numbers are also involved. But in bronze, we keep things simple and work only with real numbers. And also, we don't go into much physics, but we follow more a mathematical and computer science oriented approach, where we start with classical systems, then we move on to probabilistic systems as a generalization of classical, and finally we move on to quantum systems as a generalization of probabilistic systems. So this is the approach we will follow. Therefore, most of today's lecture will be on classical and probabilistic systems, and only at the very end we will move on to quantum circuits. And tomorrow, this is when you will really see what a qubit is, what are quantum states, what are quantum operators. This you will see tomorrow. So today we will mostly focus on classical and probabilistic. Okay, so let's start. This is the first notebook, 1-bit. If you have any questions when I talk, so please write in chat. I will stop and try to answer your questions before we move on. Okay, so let's start. So what is a bit? So you have always heard about this, like this is the smallest unit of information, etc. Actually, this is true. Like this is the smallest unit of classical information. This is how you represent information. For instance, think about a switch being on and off. And let's say if it is off, then this is 0, and if it is on, this is 1. Like this is 1 bit of information, whether switch is on and switch is off. And you can consider anything that has like 2 different states to represent 1 unit of information. Like imagine this pen. If it is up, it is 1, and if it is down, then it is 0. So this is also representing 1 bit of information. Or like, as I mentioned, anything that has 2 distinct states. And this is how we encode information in the computers we use today. We will call those classical computers to differentiate between quantum computers. And in our classical computers, how we encode information is like, right now our current computers are working with electricity. But in the past, this was not the case, for instance. But for our computers today, they have a component called transistor, and which is either on or off, depending on the electric current, voltage difference. And this is how we send and how we process information. For instance, if you if you type A on your keyboard, then what's happening behind is you are sending like a series of ones and zeros information. And this is corresponding to like transistors on, off, on, etc. I could send the same information like through a pen. So it's like I could build a computer out of a pen, out of lots of pens, let's say. But it wouldn't be like efficient. So this is why we have today like electricity and like transistors, chips, and so on. But overall, bits is the smallest unit of information, which is either 0 or 1. And so, okay, like we encode information. Let's say I encode letter A, but then we would like to process this information. This means we would like to modify this information. So to start with, let's say you have a single bit. Then there are like 4 different operators you can apply on this to modify it. Those are given here. Identity, negation, constant, 0 and constant 1. So what are those? So identity means I'm keeping the bit as it's in its own state. If it is 0, it will stay 0. If it is 1, it will stay 1. And negation is like, if it is 0, make it a 1. If it is 1, make it a 0. So it's like turning on and off. It's like a switch. And then there's constant 0 and constant 1. Constant 0 means whatever the current state, make it a 0. And constant 1 means whatever the current state, make it a 1. And those are all the possible operators you can apply. By operator, think about changing the current state. Some operation you would apply so that the current state changes. And it can change only in these 4 ways. And we will take this information and represent it in a table. Before going on to table representation, let me ask if you have any questions until now. And then, okay, let me ask you a question, which will be important later on. So, in which of those operations you can tell me what the input is if I tell you the output? So, suppose that I tell you that, okay, the output is 1. What is the input? For which operations can you tell me this? Okay, I see some answers, not, identity, identity and not. Okay, is there anyone else thinking about like in an opposite way, saying, okay, constant 0, constant 1? Yes, like the answers are right. For identity and negation, you can tell the input looking at the output. But this is not the case for constant ones. Because think about constant 0. If I tell you the output is 0, input can be 0 or input can be 1. The same is true for constant 1. If I tell you that, okay, the output is 1, you don't know what the input is. But this is not the case for identity and negation. Why is this important? Important when we move on to quantum systems. Because such operations in which you can tell the input looking at the output, they're called reversible operations. And in quantum systems, only operations that are allowed are reversible operations. So such an operation like constant 0 or constant 1 will not be allowed. This will become important when we move on to quantum systems, but don't forget about this concept. So here, identity and negation, they are reversible operations, and we will see that they have some quantum correspondence. There are also identity and negation operators in quantum systems. Okay, let's move on to table representation. So I suppose the definitions for the operations are clear. Now we will represent those operations in a table. And here, so this might be quite confused when you first start with. This is important. This is initial state. And this is final state. So from initial to final, you should look at this in this manner. So if you have initial state 0, if your operation is identity, then you will go to 0. From 0, you go to 0. From 1, you go to 1. Right? Therefore, so how we represent this? Here, if it is going to, like, instead of goes to, we write 1. And if it is not going there, we write 0. So this becomes a table for identity. So check here from state 1, I go to state 1 if this is identity. Now let's think about negation. Sorry, I couldn't write. Okay. Let's suppose that this is the table for negation. Okay, what should come here? Write in chat. So this is the table for not. I will also answer the questions. Okay, there are some zeros and there are some ones, empty sign. Okay, here is the idea. So since not is mapping 0 to 1, so not, remember, not zero, not of 0 is 1. Therefore, this means I should write a 1 here and a 0 here. And here, so 1 is mapped to 0, therefore I should write 1 and a 0 here. And this is the table representation for not. Is this clear or do you have any questions?
We have a question on Q&A. What's the difference of those two identity tables?
I will answer that.
Thank you.
Okay, let me repeat this again and then I will move on to questions. So let's start with again identity. So if you check this table, you check initial state. Okay, this is 0. Identity maps 0 to 0. Therefore, so 0 to 0, here we write 1. And it maps 1 to 1, and therefore I write here a 1. For the nuts, let me clear my drawings. We also have it here. For the nuts, so nut maps initial state 0 to 1. Therefore, here I have a 1. And it maps initial state 1 to 0. Therefore, I have a 1 here. And this is the table representation for nuts. Now, let me answer the questions, and if you still have questions, you can write. What is the difference of those two identity tables? I suppose you're asking the difference between like this goes to and empty sign. This is just an abstract representation, the first one, and the second one is the more mathematical representation, which we'll use. Those tables actually are matrices. This is what will come next. From tables, we will move on to matrices, and those will be the matrix representation of those operators. I hope this answer is fine. And like, yes, this was also mentioned in chat. Tables will lead to matrix representation, exactly. I remember another question, maybe. I guess someone asked why we have 0, constant 0, and constant 1. So we will not have those in quantum systems, as I mentioned, but those are the possible operations you could think of. This is why we are mentioning them right now, because you could define such operations, but we will not use them. Any other questions? And at the below, you can find discussions about reversibility. This we already discussed. If there are no questions, I'm moving on to next note. And now things will get like more exciting. Now we will have probabilistic bits. So we mentioned that, okay, like if you have something which has two distinct states, then you can obtain a bit. Now, if this something, imagine it's a coin like this, and like it has like heads and tails, like two different sides, right? Then we can create a bit out of this. Say heads is 0 and tails is 1. Okay, now we got a bit again. But here we can also introduce some probability inside. So imagine that like you are tossing a coin and it's a fair coin, meaning that probability of getting heads and tails, this is the same, and it's 1/2. So this means so say you toss the coin with probability 1/2, you get 0, with probability 1/2, you get heads. So now we get a probabilistic coin. And like actually, we can represent this coin tossing as a table again. So we can imagine this coin tossing as an operator and create its table. Its table will be boring. Why? Because so imagine that you have initially a coin in head state. So you can think of this as your coin's side is up, and you start tossing it. Then with probability 1/2 you get heads, and with probability 1/2 you get tails. And this is the same if like you start with coin's tails side on top. There is no difference, right? Because it doesn't matter whether initially your coin is heading up or heading down. It doesn't matter. After you toss the coin with probability 1/2, you get heads, and with probability 1/2, you get tails. Therefore, this becomes the table representation for tossing a coin. So this is initial state, and this is final state. If it's initially heads, with probability 1/2, you get heads, and with probability, you get tails. And if it's tails, with probability 1/2, you get heads, and with probability 1/2, you get tails. There's no difference. And you can here replace heads with 0 and tails with 1, and you obtain this table for tossing a fair coin. There is a question, Anil. I don't know if you can talk, but you can write in Q&A if you have a question, I think, and I will answer. Okay, what is the initial state here? Think about initial state as your coin. So put your coin on the table. If it is facing heads, then say your initial state is heads. If it's facing tails, your initial state is tails. You can imagine this like this. When this will become an like iterative process, so like you start tossing again and again, then this will make more sense, because then your initial state will be the state you obtained in the previous iteration. But currently for the initial state, you can think it like, okay, my coin is on the table, it's facing heads. Now, imagine that my coin is not fair. So let's say you get heads with probability 0.6 and tails with probability 0.4. And my question is, what will be the new table? Okay, what should come here? You can write in chat. Okay, I see a bunch of 0.6. And yes, this is correct. Here we will have 0.6. And what about here? This is probability of getting heads if you initially have a tail. So there are some answers like 0.4, but 0.6 is the correct one. Because it doesn't matter if you initially start with heads or tails, you get 0.6. This is the probability of getting a heads. Currently, it doesn't matter if you have heads or tails initially. And you can imagine what this one will be. This is the probability of getting tails. And yes, those will be 0.4. And it's also here, you can check. So this is the table for this bias coin we have created. And now we have seen a probabilistic bit, and we have seen a probabilistic operator, actually. Any questions? Okay. Now we will move on and consider kind of a game which will give us a more complicated probabilistic operator. So I will describe you a game, and as a result of this game, we will try to construct the table for this probabilistic operator. But like in the previous notebook, so also note that if our probability of getting heads and tails was 0 or 1, then this will be a deterministic state or deterministic bit, let's say. Because if you have with probability 1 heads, this means you have like always heads, and this is a deterministic bit. It's no longer probabilistic. So you can already see that probabilistic bits is kind of a generalization of deterministic bits. And deterministic bits is the case you obtain when you restrict probability to be equal to 0 or 1. So it's like probability is generalizing deterministic state systems. And now let's move on to the game. In this game, there are two different coins, actually. One is euro and one is cent. And we start with we start with flipping a euro. And after this, if we get heads, we flip euro in the next round. And if we get tails, we flip a cent in the next round. So now we have an iterative process. We are flipping the coin again and again. And okay, like we start with flipping a euro. So this corresponds to kind of to the case where we have like heads initially. Imagine that your coin is facing heads initially. So you start with flipping a euro. And so say we are flipping say we have heads and we are flipping a coin then we should flip a euro in this case. And therefore, the probability to get heads is 0.6 and probability to get tails is 0.4 in the next iteration. And now suppose that we get tails. If we get tails, if our initial state is tails, so now our initial state is what we have previously. So this is an iterative process. And if we have tails initially, then since we need to flip the sands in the next round, then we get heads with probability 0.3 and tails with probability 0.7. Therefore, this is our table representing this game. And now observe that the columns are not the same. Why? Because depending on what we get in this round, we flip something different in the next round. We flip either euro or a cent. And this depends on our initial state. And initial state is what we got in the last round. Therefore, this is what we have as our table. Any questions? Why do we consider iterative processes? Because so you have a bit and you will apply consecutively some operations on this bit. And in such a case, you will have initial state, final state, initial state, final state. So if we are doing this only once, then we have an initial state and then we have a final state. If we start with heads up, then what we will get is those probabilities 0.6 and 0.4. If we start with like tail side up, then we will get 0.3 and 0.7. Say like we did it once, okay. But like if you imagine that you are doing this consecutively, because this will correspond to applying operations on a bit and process it. So imagine your computer, your computers are always applying some operations in the like arithmetic logic unit, etc. So we will do this consecutively. And in such a case, your initial state is what your final state is in the previous state. Because like, okay, I have heads and now I flip it and again I get heads. Then, okay, now this is my initial state. I flipped again and so on. Does Markov chain operations? Exactly, this is a Markov chain if you know about it. What we are defining here is exactly a Markov chain. I will not go into details, but exactly. In the case of Euro and set, the initial systems are different, right? That's why we are getting different probabilities. It's not correct to say initial states are different, but it's better to say what we flip depends on our initial state. So the probabilities are different depending on our initial state. This is the difference from the previous notebook. Depending on the initial state, you get different probabilities because you throw different coins. So please try to ask your questions through Q&A. But say when I ask you some question and I ask you to type in chat, then you can type in directly in chat. But if you didn't understand something and if you want to ask it, just type it in Q&A so it will be easier to track this way. And like you can ask any questions if you don't understand something. Okay, and here's a task. And here in this task, you are required to track what's going on with the probabilities. Actually, this is not a task, but you have a task below. This is just, I will now run the cell to trace what's going on with the probabilities at each stage and how it is changing at each stage, the probability of getting a heads or probability of getting a tails. So initially, we start with a euro, and I mentioned you that this is equivalent to thinking that initially we have heads side up. So initially, probability of heads is equal to 1 and probability of tails is equal to 0. This is what you have initially. And what is the new probability of getting head? It will be 0.6, right? You can see this. Initially, I have 0. I start here. I have heads. And I'm flipping my coin. The probability of getting heads is 0.6. And probability of getting tails, it will be 0.4. I suppose this is clear, right? For the initial state. Anil, you can type in Q&A if you have a question. Now, I will ask you something else, and I will want you to think about this. What is the probability that I get tails in the second round? Our table never changes. Our table is fixed. But depending on our initial state, we look at different column of the table. You can imagine this like that. And let me repeat my question. My question is, what is the probability of getting tails in the second iteration? Okay, okay, let's go over it together. So I asked you about probability of getting tails in the second iteration. So first of all, let's think about the first iteration. In the first iteration, I can get head or tails, right? So having tails in the second iteration, this corresponds to two different cases actually. It corresponds to getting heads in the first iteration and getting a tails in the second iteration. Or it can be that we get tails and tails again, right? There are two different ways that we can get tails in the second iteration. Actually, I didn't calculate it yet, so there are some answers in the chat, but I just also wanted to think you about it. So if we get heads in the first iteration and tails in the first iteration, this will be with probability 0.6 times tails from getting a heads 0.4. Why? Because we start with head. I throw the coin, I get head. This is with probability 0.6. And then I get a tail. So this is tail from head. This means 0.4. And what is getting two tails consecutively? So since I start from head, probability of getting tail is 0.3. And getting a tail again, this happens with 0.7. And if you would like to get the total probability, you should sum those two numbers. So I think it is 0.48. Or no, wait, 24, 21, it should be 0.45, yes, 45. And if we do the same for getting heads in the second iteration, this will be 1 minus this probability. You can check. It should be like probability of heads plus tails, heads. And what is heads times heads? It's 0.6 times 0.6. And what is getting tails and then heads? This is 0.3 times 0.3, right? No, wait, tails. From heads, I get tails. No, it's 0.4 times 0.3. I'm checking if I did anything wrong. There's tails. From tails, I get heads. Because tails. Here I think I have a mistake in the previous one. This will be 0.4, I think. Yes. Because this is tail from heads. And then, oh no, okay, let me delete this. Okay, let me type it here again. First we get tail from heads. This is 0.4. And then we get tail from tails. This is 0.7. Okay. Anyway, like what I want to give you the idea here is how we are going to trace this information. It will be much simpler than this. Yes, thank you. You also corrected me. TT was wrong. There's a question in Q&A. Yes, initial status heads, exactly. So we will trace this through matrix representation, vector and matrix multiplication. This is where I want to move on actually. All these combinations, all this information will be provided us within vector matrix multiplication. And this is where those tables will be useful. Here is a code of what we did, actually. So probability of heads is currently 1. This is the initial state. So new probability of heads is your current probability of heads times 0.6. This was 1 in our case. Why? Because probability of heads is equal to 1. And this we didn't take it into account because this was 0 in our case. But this will be important in the next iteration. You will see why. And similarly, our probability of tail is our current probability of heads. So this is like getting tails out of heads plus getting tails out of tails. This is exactly what this is, what we did here, actually. So this is doing this iteratively. Like if you calculate those, at this stage, your probability of head is 0.4 and your probability of tails is 0.4. Like this is after one iteration. If you flip the coin once, then what are your new probability of heads and tails in the second iteration? We calculated this one here. And this is exactly 0.6 times 0.4 plus 0.4 times 0.7. And this is your new probability of getting tails, which means probability of getting tails in the second iteration. And this one here, this is what we did here. Probability of getting heads in the second iteration. And actually this equation gives you the next probabilities. You can always calculate the next one. And from this, we will move on to matrix and vector representation. Because you will see that this is really what's happening if you trace vector matrix multiplication. But the logic behind is what I showed you here, like getting tails. Okay, you can get heads in the first iteration, tails in the first iteration. But imagine that you are doing this for 10 tosses. Then you should be calculating all like probabilities. But it will be enough to consider only your previous probabilities of heads and tails. And then all you will use is this information. What is my probability of getting heads from heads, tails from heads, tails from tails, heads from tails? And this is your table. Let me move on to next notebook. And I think it's, okay, it's here. So we will come back to this. And if you have any doubts right now, this will become clear when we move on to this notebook, where we move on to this matrix vector multiplication idea. Let's give a break for this right now. Let me clear my screen. And let me talk a little bit about probabilistic states and how we will represent probabilistic states. So imagine a state, a probabilistic state. Say it's like you throw a fair coin, okay, and you have probability of 0.5 for heads and 0.5 for tails. We will represent this using a column representation like this. 1/2 and 1/2. And here, this is probability of 0 and this is probability of 1. So after a fair coin flip, with probability 1/2, you have state 0. With probability 1/2, you have state 1. This is how you read this column representation. Here is another example. Let's check here. Suppose that now you have a biased coin. So that probability of getting heads is like 3 times getting a tails. Then after flipping this coin, your state representation will be this column vector, 0.75 and 0.25. So this gives you probability for state 0, and the second entry gives you probability for state 1. You might wonder, why is it like this? Can't we do the converse? This is the convention we will use. Of course, you could like switch everything, but then remember our table representations, you would need to switch those as well. So this is the convention. First comes 0 and then comes 1. Any questions? Let me ask you a question. What does this column vector represent? You can type in chat. This is not an operator, so don't mix the two. This is, so we use columns to represent states. So it's not an operator, or it's not an operator representation. So this is exactly the 0 state. It is a deterministic state. So this means you have with probability 1 kind of heads. And this is also representation for deterministic state, which is equal to 0. It is not constant 0, so don't mix that. So it was an operator, but this is a state. We always get heads. I'm not sure if this is the correct way to say it, because this is like the head state. It's not that we are getting something. It's not an operator. It's a state. Probability of 0 equal to 1. Yes, exactly. Probability of getting 0 is equal to 1. Probability of getting 1 is equal to 0. So this is how we will represent 0 state. And similarly, if I have column representation 0, 1, this will be my state 1, representation for state 1. And this will be the same also in quantum systems, this representation. Therefore, this is quite important. So this is exactly the 0 state. And this is the 1 state. And you will see why this column representation is useful. Any questions before we move on? You can type in Q&A. Okay. And like so far we were working with only bits with 2 states. But now imagine that. So maybe let's start from here. For instance, think about a dice, which has 4 sides. Then, how would you represent this? Represent this as a column vector. How many entries will you need? Can we represent this with 2 entries? No. 4? I'm not sure. Why? Because now if you have a dice and if it has 6 distinct states, then to represent probability of getting each one of those states, you need 6 entries. And those entries, each one will correspond to getting that state's probability. I mean, for instance, we can check the solution here and I can show you here. Okay, no problem. If you have a, yes, exactly. If you have a 4-sided die, then I don't know how this happens, but like, this will be like in, yes, in some particular shape, then you will need 4 entries in your vector. Okay, I can move to here. If you have 4 states, 4 distinguishable states, then you would use vectors with 4 entries to represent that state. Those ones which involve only 0 and 1, like the ones I showed you for state 0 and 1, those are also called like basis vectors. And right now those 4, they correspond to deterministic states. So you can think about this like with probability 1, you get state 0, with probability 1, you get state 1. You are in, not get, but let's say you are in state 1. So this is state representation, it's not operator, sorry. I shouldn't say get. You are in state 2, and you are in state 3. And for instance, if you have a system where with probability 0.2 you are in state 0, with probability 0.25 you are in state 1, and so on, this would be your state representation. And you can see here immediately something more. This is a linear combination of those basis vectors. And this will be always true, whether you have 4 distinguishable states, whether you have 2 distinguishable states. It will be always a linear combination of those basis vectors, like state 0 and state 1. So remember the example, first example we had. like 0.5, 0.5. In this case, for instance, you can write this as like 1/2 times 1, 0 plus 1/2, 0, 1. So it's like with probability 1/2, we are in state 0. With probability 1/2, we are in state 1. This is how you can think about this. And it's a linear combination of those deterministic basis states. And for a system with 4 states, this is the same. It's again a linear combination of those 4 basis vectors. Now I have a question for you. What is your observation about this vector? For instance, can we have minus sign inside? Okay, let me check the answers. Always positive. It may be better to say non-negative, always. Since those are probabilities, exactly. They should be always non-negative. And there was an answer. I think like column sum should be equal to 1, always. Why? Because this is defining probabilities your system is in. And probability always adds up to 1. So always column sum is equal to 1. And you can also see how this state is generalizing deterministic one. In deterministic, you can either have 1, 0 or 0, 1. Again, those are non-negative and sum is equal to 1. But in probabilistic, now it's more flexible. You're allowing non-negative entries, not only 0 and 1. But column, still it should add up to 1. Such vectors, they're also called stochastic vectors, if you maybe heard about it. But this is the overall idea that like to represent a probabilistic system, or a probabilistic state, you need a column vector which has entries as many as there are distinct states, and those entries, they represent probabilities. Any questions? Okay, I hope all is fine. Let's give a 10-minute break and let's meet back at 15:10. And we will continue from the next note. Okay, so see you in 10 minutes. So we're back. We were discussing properties of probabilistic states, their column vector representation, and we have observed that they should always sum up to 1 and they should have non-negative entries. Okay, now let's move on to probabilistic operators. Now, remember, this was the operator for this game, where we were flipping two different coins based on the outcome of the coin toss. And now we are going to try to represent this through column and matrix representation. So we were starting with heads, remember. And this means initially we are in state 0, and which we have this vector representation, 1 and 0. So this is our current state. And now we have this table representation, remember, for this coin flip. And now, remember how we were calculating the next probability. What we were doing was, okay, we are in heads and with probability 1. So the probability of getting heads in the next stage is equal to 0.6 times 1. Since we didn't have any probability of tails, this is equal to 0. And probability of getting tails in the next round is equivalent to 0.4 times 1. Why? Because with probability 1, we are in heads. And it's 0 times 0.7. And if you check here, this is actually this multiplication of this table with this state. Multiplication of this matrix with this column vector. So 0.6 times 1 plus 0.6, 0.3 times 0. And this multiplication gives you the next, gives you the state of the next state. And this becomes more evident if you check the next one. Because here, remember, this was the calculation we had made by checking case by case. And actually, so what we have is probability of being in heads, 0.6 times probability of getting heads here, plus probability of being in tails times probability of getting heads, which is 0.3 times 0.4. And this gives us the probability of getting heads in the next step. So with probability 0.48, after the second iteration, we are in state 0. We are in state heads. And similarly, if you like multiply this row with this column, then you get the second entry. So this example shows us that we can trace behavior of probabilistic systems through vector matrix multiplication. We represent our states by vectors, column vectors, and we represent our operators by matrices. And by multiplying our vector by a matrix from the left, we can trace our system's current state. So this game, like in the previous notebook, we had this to give you this idea of evolution, how probabilistic systems evolve. Any questions? So likewise, like we had some conditions on the probabilistic states, right? They should be non-negative, they should be, their column subs should add up to 1, etc. Similarly, we have some restrictions on probabilistic operators. Why? We need this because a probabilistic operator should transform a probabilistic state into another probabilistic state. For instance, imagine an operator, and after multiplying this with your current vector, you get a minus sign. Or you get a column vector which is not adding up to 1. This means your operator is not a probabilistic operator. Why? Because applying this, you are not getting a probabilistic system anymore. So therefore, probabilistic operators should also obey some rules. Do you have any ideas? What should be the rule for a matrix to be a probabilistic operator? Must be invertible. Actually, this is not correct. Remember the first operator we had, fair coin flip. This is also a probabilistic operator, but it's not invertible. So they don't need to be invertible actually. No zeros and ones. This is also not totally correct because deterministic operators are also probabilistic operators, kind of. They are probabilistic operators which involve probability 1 and 0. So this is also possible. Such an operator will be also counted a probabilistic operator. Sum of columns equal to 1. Yes, this is what we need. Why? Because think about what this table represents, each column. So this first column is representing your next probabilities. Starting from an initial state, what are your possibilities? And this should sum up to 1, exactly. Because otherwise, thinking about the intuition, what this table represents, this wouldn't work. And also, if you had such an operator whose column sum is not equal to 1, then you wouldn't end up again in a probabilistic state, like shown here. And there's one more thing actually. And it is that each entry should be non-negative. Why? Because again, by intuition, those are representing probabilities. So any operator in which all entries are non-negative and the summation of column is equal to 1, it's a probabilistic operator. And this evolution, it is linear. And you can trace this through matrix vector multiplication. Any questions? Okay. If there are no questions, I'm moving to two probabilistic bits. So far we have considered a single bit, or we also considered a system with more than 2 states, but now we are going to combine 2 probabilistic bits. Now imagine that we have 2 probabilistic bits, which are in those 2 states. So this is our first bit, and this is our second bit. Now there are 4 different possibilities we can have. What are those? Both can be in state 0, both can be in state 1. It can be that first one is in state 0 and second one is in state 1. And it can be also that first one is in state 1 and second one is in state 0. For instance, can you tell me the probability that both bits are in state 0? Yes, exactly. This probability is equal to 0.12. How we obtain this? We multiply 0.2 with 0.6. Why? Because probability of first bit being in state 0 times probability of second bit being in state 0, which is equal to 0.12. What is probability of being in 0, 1? Yes, it's 0.08. So you get the idea. In this notebook, we will generalize this notion in terms of vectors. So we will see what we should do to get this new vector representation. But let me ask you, how many entries do we need to represent 2 bits, state of 2 bits? Yes, we need 4 entries. Why? Because we have 4 distinct states. And we already started constructing this vector. You said this should be 0.12. And this should be 0.08. I couldn't write it. It's like ugly, but okay, 0.08, 0.48. And here we have 0.32. And you can check that the sum is equal to 1 again. And this will be the representation of our new combined state. So this is representing 0, 0, 0, 1, 1, 0, and 1, 1. And if you read those in binary, you'll see that we have 0, 1, 2, and 3. So it is as if like you have a system with 4 distinct states, and those are the probabilities. And we obtain this 4-state system out of 2 distinct 1-bit system with 2 states each. Any questions so far? Now we will see mathematically what operation we need to obtain this vector. Okay, like we did this multiplication. You can see this, but let's check. First of all, we will introduce some new notation, which we will also use in quantum systems. So this notebook is really important to understand also what will happen with multiple quantum bits, actually. So remember, this is the vector representation for state 0. This is the vector representation for state 1. We will use this notation to represent state 0 and this to represent state 1. Why? Because first of all, when you have when you have systems with lots of states, you will see that it's no longer really convenient to write really long vectors, but this notation will be really easy. And it's really easy to read such notation. For instance, this state 0.2, 0.8, you write it like this, 0.2 times 0 plus 0.8 times 1. And here this coefficient gives you the probability of being in state 0. And this is probability of being in state 1. And similarly, you can check this one. And this is actually like, if you like do this, remember this linear combination idea? If you replace this 0 with 1, 0 vector, this is what you get. So just another notation, basically. Any questions about this notation? Okay. Now, suppose that this is your first system and this is your second system. Now we will combine those, and the operation to combine such systems is tensor product. And tensor product has some rules. So for instance, if you apply tensor product to such two states, this is what you get. So tensor product is used to obtain larger systems, kind of. And when you apply tensor product, this is what you get. So first of all, it distributes over addition, like multiplication over addition. Therefore, we have this. From this, we get 0.12. And then we combine the states. Check what I have. 0.1200 plus. Then I have this two. 0.08. And I have 0.1. And remember the probabilities we have calculated. Those are exactly the probabilities we had. So mathematically, combining two systems corresponds to tensor product. So to obtain new states representation, mathematical representation, you will apply tensor product. So this is the idea. I will not do the rest, but you see the idea. So it's 0.4810 and 0.3211. And if you apply tensor product to the vector representation, again, you will obtain the same representation. Okay, this is task 4. I will show you there. Let me clear this. So there are multiple ways to obtain the same thing. You can either use this representation. You can directly use vector representation. Okay, now check this. This is the rule for tensor product of vectors. So you take this entry and you multiply this vector. You put it here. And you get this entry, sorry, 0.8. And you multiply your vector. And this is your new vector representation for 2 bits, 4 probabilistic bits. And it has 4 states. And this is exactly what you get if you follow this state representation. And can you imagine what is the vector representation for state 0, 0? I mentioned you this already, actually. Yes, it's 1, 0, 0, 0. And you can guess that this one is 0, 1, 0, 0. This one is 0, 0, 1, 0. And this one is finally 0, 0, 0, 1. And if you write those, you will get a linear combination and you will exactly get this vector. And furthermore, you can prove that this is the vector representation for this state using this tensor product. Why? Because state 0, tensor product state 0, and this is your new vector representation for state 0, 0. So it's like everything is like fitting into their places. So this tensor product is really letting us construct composite systems which are composed of multiple probabilistic bits or multiple deterministic bits. It's the same. Probabilistic is just a generalization of the deterministic one. And you will see that it's the same for quantum systems. Just like the rules for being a quantum state and being a quantum operator, those two will change. Any questions? Can we say that the resultant probabilistic state has still information from initial probabilistic states? If you're asking whether we can decompose this back, then I will say no, because you could obtain same state from two different inputs. But this depends on what you think about when you say have still information. But you will see that. So we will not go into this into probabilistic systems, but you will see this in quantum systems. There are some states which you cannot decompose. So for instance, given this can be decomposed into two subsystems, right? So you can decompose this system with four states into two subsystems with two states. But you will see that for some states, this is not the case. They cannot be decomposed like this. They cannot be written as tensor product of two smaller states. Any questions? We will move on to something new. Because right now we are finishing this part. I am not going on to this one and this one. If you want, you can check those. I will move on to this part if you don't have any more questions. Okay then. So this notebook is about some experiments performed with a photon. So remember that I told you you can take anything that has two distinct states as a photon. This can as a bit, sorry. Actually, like photon also has two different states, and we can take a photon as our bit, or let's say as our coin in this case. So photon will be our coin, and there is a physical apparatus called beam splitter. Now I'm talking about something physical. So far we have been talking about something more abstract, like operators, matrices, etc. Now we are talking about something really physical. There is a photon source. There's something called beam splitter, and this is kind of a coin flipper. Why? Because when a photon comes, with probability 1/2, it gets reflected. So this is like heads. And with probability 1/2, it gets transmitted. So like heads, tails. And this is happening with probability 1/2. So instead of a coin, we are taking a photon. And instead of coin flip operation, we are performing beam splitter operation. And we will see what will happen. So this is the setup. And when sending a photon, so you repeat this many times. So imagine I give you a coin and you flip this many times. And as a result of flipping this coin many times, you will collect some statistics, right? And the statistics will tell you, okay, like, say 48 times you get heads and 52 times you get tails. And from this, you can deduce that, okay, like heads and tails, this should be with probability 1/2. And if you repeat the number of experiments, number of coin tosses, the more likely that you will obtain the real probabilities. There was a task in coin flipping notebook, but like I didn't mention this. But the more you simulate an experiment, the better estimation you will get. And in this experiment, we are sending photon like many times, and we observe that half of the times it is transmitted and half of the times it is reflected. And we will say that like this is transmission is state 0 and reflection is state 1. And like this is the first experiment. We are sending the photon. It's getting half of the time reflected, half of the time transmitted. And the initial state, we will say that it's state 0. So it's coming like as it is transmitted this way. And then you will do a second experiment. In the second experiment, now we have 2 coin flips. But like check the scenario. Here we have like 3 photon detectors. So photon is coming here. Then we have a beam splitter here, a coin flipping. And then here there is a mirror. So it's coming here. And there is one more coin flipping state. Now, what is the probability that photon will be observed in this A? Yes, it's 1/2. Why? Because there's a coin flipping here, like this beam splitter. And to be consistent with this experiment, it should be that with probability 1/2, we observe it here in A. Now, what is the probability for B1? Yes, and the same will be for B2, right? So we expect that with probability 1/2, it ends up in A. With probability 1/4, it ends up in B1 or B2, right? Like this is our expectation. And this is correct. If you do this experiment, this is what you will observe. Now we have another experiment. This time, we have again 2 coin flips, but check the like system. Photon is coming to here. Then there's a coin flip. And then it's getting reflected from this mirror. And there is one more coin flip here. So it can go like this way and this way. So this way and this way. So this way and this way. And then this way and this way. Like very similar to flipping 2 coin tosses, right? Like heads, 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 tails, tails, heads, tails, tails. Now, what is the probability that the photon will end up in B1? Okay, many answers are like 0.5. There is one 0.025, 0.25. Is symmetrical 0.5. So actually you are right. If this was like behaving really like a coin flip, then this is what we would expect, right? 0.5 here and 0.5 here. But, and like here you can check the math, right? So we are starting in state 1, 0. And then if this is the coin flip operator, which is this matrix, remember, we had seen this before. Then your new state is 1/2, 1/2. And if you apply this once again you will get 1/2, 1/2. Like this is the mathematical explanation we would have. However, so despite this is our prediction, if you do the experiment, this is what happens. So with probability 1, it's ending here. And it's ending here with probability 0. So you never observe the photon here in B2. But then, like, what's happening here? What's the problem? So the thing is here, we are not using a coin, but we are using a photon. And therefore, this is not behaving as we would expect in a probabilistic system. this is behaving in a quantum way, which we have not seen so yet. And the thing is, actually, this coin flipping here, it's not behaving as our fair coin flip toss. And like, this is not something we can explain with classical mechanics, classical physics we know, like the probabilistic systems. And to explain this, you need to understand what's happening with quantum systems. And why? Because photon is something for which classical physics is no longer working. You should think with quantum physics and with rules of quantum physics. Therefore, our interpretation that, okay, like this is a fair coin flip and this is a probabilistic bit, this is not correct. And what is the correct interpretation? This you will see tomorrow. I will not explain this today. But if you have some like pre-knowledge about quantum systems, you will see that this is corresponding to an Hadamard operation whose matrix will involve some minus entries, some negative entries. And this will explain how we can have probability 1 and probability 0 here. But this, I will leave it right now. So this is for like tomorrow. And from this, we will move on to writing a quantum program. Now, this is where we will for the first time see how a quantum program looks like. But before we move on, so first of all, this notebook will be not really related to what we have seen so far. And as I mentioned, the explanation of this notebook with photos, this will come tomorrow. And let me tell you first, before we move on to details, what is quantum programming and how we do this. So quantum computers, like let's say quantum computing, there are different approaches, and here we are using gate-based approach. And in this approach, there are some bits, and we will apply some gates. If you, I don't know about classical gates, there are also classical gates, but this is very low-level programming. You can apply NOT, you can apply, I don't know, XOR gate, etc. But currently, with our modern modern classical programs, we never think about gate-level programming. We write for, we write if, etc. But like in the very low level, still there are some like gate operations going on. And this is what we do with quantum programming. It's low level. We have some bits. They will be quantum bits. And we will process them. We will modify them through what we call gates. And those gates are actually some operators, some linear operators. They have some matrix representations mathematically, if you think about it. And physically, what's going on? So we are not dealing here with hardware or physics in this tutorial, but physically there are different ways to build a quantum computer. There are like superconducting qubits, there are like ion traps, or there are photonic ones as we have seen. So the idea is the following. If as a bit you take some particle which has quantum physics properties, then you obtain a quantum computer. And your bit is no longer a classical bit, but it's a quantum bit, it's a qubit. So if we replace, like if instead of like transistor, you take a photon and you try to build a computer out of this photon. Say you have many photons, they can be in state 0, they can be in state 1, which corresponds to being in reflected or transmitted state. And you can apply some operation on the photon, like the beam splitter you have seen. There are also some other physical operations. Then what you would obtain is a quantum computer. And quantum computing is basically computation which is performed with such quantum bits. And it has some special properties which are different than classical computation. Why? Because your bit now has some different properties, quantum properties, unlike the classical bits, like superposition and entanglement we will see. Therefore, this is what differentiates the classical and quantum computation, classical computers and quantum computers. And in this tutorial, we are learning how to program quantum computers that work with quantum bits. And as I mentioned previously, we will have some quantum bits and we will modify those through some gates. And mathematically, this will correspond to having some vectors and modifying them through some matrices. And matrices will be the mathematical operation to represent those gates. There is a question, what was the reason to think classical bits are not enough? In other words, why we need quantum computing? A good question. So the initial idea of quantum computers actually arises from the following. So suppose that you want to simulate behavior of some chemical system, some molecules. Those are behaving according to quantum physics laws. And Feynman thought that it will be more natural to simulate nature through quantum computers which also behave according to quantum physics rules. Because the system you would like to simulate is obeying quantum rules. But your classical computer, is obeying classical physics rules. And it is difficult to simulate a quantum system with a classical computer. Why? Because we will see that you need exponentially many larger number of states. Because you will see that to represent like 2 bits of information, you need to store 2 to the 2, like 4 states, 4 bits of information. And similarly to like simulate n bits of quantum information, you will need 2 to the n sized vector. And this makes simulation of quantum systems harder with classical systems. So this was the first idea. And then after this idea came out, people realized that using quantum computing, some tasks can be done much more efficiently than they can be done classically. Like there are some first algorithms like Grover's search, factoring, which we will see here. So we will not see factorization, sorry, we will see Grover's search. But like Peter Shor came with this algorithm for factorization. So there are no efficient known algorithms for factorization classically, but he came up with a quantum algorithm to solve factorization problem. So this is why people thought, okay, maybe we can find some other use cases as well, where we can have some efficiency to use quantum computers rather than classical computers. This does not mean that quantum computers solve all problems efficiently, but there are some problems which quantum computers can solve more efficiently than classical computers. So that's the idea. Okay, now let me move on. So we are using a framework called Qiskit. This is provided by IBM. And now you will see how we design a quantum circuit with a single qubit. So there are some imports you need to make, like quantum register, classical register, and quantum circuit. I will explain each one. Here we are creating a quantum register. This one specifies that it will have a single qubit. And this QREG is its name. This is not necessary. You may not provide this. You can do this. And in each quantum circuit, if you would like to read out something at the end, you will need a classical register as well. And you will see this why tomorrow probably. Always you need to make a measurement at the end. There is some concept called measurement, and the result of the measurement will be written on classical register. This measurement can be taught like this detector here. So you need to detect the result, kind of. Classically, you might think that you need to read output of the coin flip, let's say. And then you create a quantum circuit, giving it as parameters the quantum and the classical registers. Now, this is our quantum circuit. And we will apply an operation you already know called NOT. And remember, I told you that NOT is a reversible operator. Therefore, it's also a quantum operator, which you can apply on quantum bits. Currently, the circuit we constructed is actually doing something really classical. I forgot to tell you, but qubits always start in state 0. So we have a system, we have a single qubit starting in state 0. We're applying a NOT operator on it, and this is how you apply a NOT operator by writing like dot x. And here you give the qubit on which NOT operator should be applied. And then there's an instruction called here measure. And this will measure the quantum circuit and write the result. So it will measure qubit 0 and write the result on classical registers, qubit number 0. Now I run this cell. And then we will visualize it. Okay. So this is the visualization. This is it looks nicer if you write here MPL. So we have a quantum register, we have a classical register, we have a single qubit. You see a single line here representing the qubit. We're applying NOT gate, we are measuring, and we are writing the result here on the classical register, qubit number 0. This doesn't mean that the output is 0. So it means that we are writing the result on qubit, classical bit 0. So we constructed our circuit. We start in state 0, and in quantum mechanics, this is expressed as cat 0, like this. And after applying NOT gate, we expect our bit to be in state 1, right? You know this from classical systems. And in quantum physics, we write this as cat 1. So this is what we expect to see after running this circuit, and this is how we execute the circuit. Here we call this method called execute, and we provide a backend. So in this tutorial, we are going to use always a simulator, meaning that it will simulate the behavior of a quantum computer. We will simulate a quantum computer. We are not connecting here to a real quantum computer. And this backend is the device on which you would like to run your experiment on. If you are interested, you can check IBM's webpage and connect to a real quantum computer and run your circuit on a real quantum computer. But right now, this is simulated. And this shots, it is a number of times we are doing this experiment. So think about like coin flip. It's like you are flipping the coin 1000 times. And then here we use like get counts to get the result. It gives you a dictionary. Since this is a NOT gate, and since this is something deterministic, what we get is 1 for 1024 times. Why? Because it doesn't change. Anytime you apply this NOT operator, you should get 1 as your output. It's not something probabilistic. Therefore, here we get as the output 1024 times F1. But if you would like do this on a real quantum computer, it may be that you don't get always a 1. And the reason is there is noise on real quantum computers. So the output is not totally, like, let's say, pure. It includes some noise. Therefore, you will get a dictionary, for instance, which gets 62 times 0 and 962 times 1. But this is due to noise. Mathematically, what you should get is the following. And actually, you can trace this mathematically as follows. You start in state 0, right? This is the vector. And recall the table representation for knots. Let me show you. This is the table representation for knots. So it's like this. So if you apply this, let's change the, okay. We were in this page. Okay. If you do this multiplication, you will get this state. And this is cat 0. This is cat 1. And this is the not operator. And you can also print a histogram. But in this case, it's not really exciting. It's all ones. And this is our output. Any questions so far? Okay. I'm waiting for the question. Why do we draw quantum circuit? Visualization is always good to see what you are doing, what's happening, what's going on. For instance, when you work with more complicated circuits, it's just like something nice to have. If you draw the circuit, you see what you're doing, but you don't need to, of course. It's not required. Let me ask you a question. Suppose I applied not twice. Okay, I construct such a circuit. See, like I apply this not twice. Let me run this. Okay, let's visualize it. See, we are applying not twice. What is the expected output here? Okay, there are two answers, 0. Any other ideas? There is a 1. Okay. Okay, there are two ones, so it's like a tie. 2 zeros and 2 ones. Three ones. Can you write why do you think we will get 1 in chat? Let me show you the results. It's 0. And if you think why, so you can check this mathematically first. This is the first option. After first application of this knot, we were in this state, right? And if you apply this the not operator one more time, what you would get is 1, 0. This is one way to see this. Another way is the following. You start with 0 and you apply a not and you get a 1. If you apply not on state 1, then you get a 0 again. This is another way to see it. A third way to see this is the following. Actually, we are applying not twice on state 0. So it's like not square applied on 0. If you multiply this matrix with itself, you will get identity. So actually, not is its own inverse. That's the third way to see this. And by intuition, like this is more intuitive, like this state representation from 0 you get 1, from 1 you get 0. Yes, exactly as Gergely has written here. So we get again like 0, 1024 times. By the way, let me explain why we are running this multiple times. We are getting the same thing here, so it is not really interesting, but remember that quantum systems will be probabilistic. They will not be deterministic. So therefore, like as if you are tossing a coin, you will need to repeat the same experiment more than once to collect a statistics of the outcomes. This is why we need multiple number of shots. In this example, it will be enough if we had run this only once, because like this is something deterministic happening right now. We have not introduced a real quantum operator. So the not operator is a deterministic operator, but it's again a quantum operator, the one we are currently using. Any questions about this example we have discussed? Sure, let me go to the circuit diagram. I didn't run this again, but okay, this is how it looks like. We didn't get a 0 in the first run. When we have a single not, let me construct this and run this again. If you're asking about the 0, this is not the outcome. This is where the qubit is, the outcome is stored. It's not the output. You get output only after executing the circuit here by counts. And it is 1. Okay. Now we will see a like quantum circuit with multiple qubits, and then we will finish for today. There is an explanation about chiasm language. So this is even a more lower level language, and you can get to like this code for your circuit. You can read about this here. Now I will move on to quantum circuit with multiple quantum bits. Here we construct a quantum circuit with 4 qubits and 4 classical bits. So here we provide 4 as our input. And we apply xk to first quantum bit twice. Then we apply this once to qubit number 3, and 3 times to qubit number 2, and like 4 times to qubit number 1. Can you tell me what the output will be? So check here, like it's not going in the order, like 0, 3, 2, 1. Okay, we have an answer 0, 0, 1, 1. Other answers? Okay. Okay, let's run this and see. Here there is something called barrier. Currently we are using this only for visualization. This will just put, I will show you right now. On the circuit, it will put some line before the measurement. We are measuring our quantum register on the classical register. Okay, let's draw. Okay, like we have qubit number 0, 1, 2, and 3. We apply twice, 4 times, 3 times, and once. So since this is even number of times, we expect to see 0, 0, 1, and 1. And this was the answer you gave. And check here right now, like 0, 1, 2, 3. Those are the classical bit numbers. Let's execute and draw this. We get 1, 1, 0, 0. Now, why it is like this? Because in Qiskit, the qubits are ordered starting from right to left. This might be confusing at the beginning. So you should read this like qubit number 0. So actually you were right. But in the output, how you see this is qubit 0, qubit 1, qubit 2, and qubit number 3. You may ask why it is like this. When you read it in this way, so it's about where is the significant bit, where it is, whether it is on the right and whether it is on the left. This has a nice interpretation that you can this state in binary as, for instance, 30. Like here you see an example. And this will become more meaningful when you start writing more complicated quantum programs. But like this is Qiskit convention. And therefore, whenever you are executing a circuit, you should be careful about this. It's not that you were wrong. It's just that the output is kind of like reverse of what we think. So in our notebooks, we try to say qubit number 0, qubit number 1, qubit number 2, instead of saying first qubit, second qubit, because this is confusing. I will also try to be careful with this. There is an option to reverse the bits when drawing, by the way. Like you can draw it this way, 3, 2, 1, 0. And then this will be like 1, 1, 0, 0. This is but just for visualization, don't forget. It's not for printing it in the reverse way. It's just for visualization. If this will help you, I don't know. But otherwise, like this is the Qiskit's reading order, like this. 3, 2, 1, 0. Any questions? Output is going to be in right hand order. Yes, this is how the output will be always. So you should read this in this way. So we should expect in this case, for instance, 1, 1, 0, 0, not 0, 0, 1, 1. Any questions? Okay then. This is all for today. So in the program, I see that there's a Q&A session today on Discord at 9 p.m. Turkish time. And you can also ask any questions if you have in Discord. I again strongly advise you that you try to complete the tasks in the notebooks, even though like we will not check this. To get the certificate, the important thing is to complete the homeworks on time. And like tomorrow, you will continue with Sabah, with quantum bits, quantum states, position and measurements, and quantum operators. Sevil, do you want to add anything?
No, thank you. I would like to thank you very much to you for the informative session on Introduction to Quantum Computing, quantum programming, actually. And see you all tomorrow.
Thank you. See you. See you on Wednesday, and Sabah will be here tomorrow. See you then.
We have a question on Q&A.
Okay. Let me check. Does the barrier have a waiting function until all the operations are completed? Okay, let me show it here. So for this example, we don't see any impact on the circuit, but imagine that there was some other gate here. This would wait until all those gates have been performed and then apply this gate afterwards, if we have a barrier in between. So mostly we use this in this tutorial for visualization. But this could have really a impact on the circuit. Let's say let's say there is a gate here, which is involving two qubits, both this one and this one. So this is changing. If you don't put a barrier, but again, okay, if I first write C naught, this will not have an impact. Okay, I cannot readily give you an example which would have an impact, but as you said, it waits until all the other gates are executed and then applies the next gate. But we will use this mostly for visualization. Okay, I think that's all. And thank you.
Thank you so much. See you tomorrow.